Hello and welcome to this recorded e-learning on CLB Architecture for the Xilinx 7th Series of FPGA Products Part 1. My name is Frank Nelson. I'll be your instructor for this module. This module introduces SLICE resources available in the 7th Series of FPGAs. This basic FPGA architecture module limits its scope to discussing the SLICE resources. Now please note that there are also corresponding memory resources, clocking resources, and I/O resources recorded e-learning modules available to you as well. After completing this module, you'll be able to describe the CLB arrangement and routing resources available in the 7th Series FPGA products. You'll also be able to describe the contents of the CLB and the SLICE resources that are available to our users. Now we have segmented the content of this module into discussions on CLB structure and routing resources, SLICE resources, distributed RAM and the shift register LUT functionality, as well as how to use the SLICE resources in your FPGA. Now this content is also broken up, of course, into two different recordings. So again, to get part of this, you'll have to listen to part 2. Now the Virtex 6 and 7 series of Xilinx FPGAs contain essentially the same CLB logic resources. So if you're used to working with Virtex 6, the adaptation to the 7 series is actually pretty easy. Now slices are grouped into configurable logic blocks or CLBs and contain combinatorial logic as well as register resources. As you can see from this picture, there are a lot of CLBs on the die. While each device family is offered with a different number of CLBs, determining which density is right for your application often requires you to at least synthesize your design before choosing an appropriate density of FPGA. Only with some experience can you properly estimate how many slice resources will be necessary for your design without at least synthesizing the design first. The SLICE resources are the most essential and fundamental to an FPGA design. They include LUTs and registers. LUTs are built to create your combinatorial logic resources, and each has an associated register with it. The LUTs and the registers are grouped into slices, which also have other resources embedded in the CLB. Besides LUTs and registers, slices also have carry logic resources, which are designed to implement arithmetic logic functions with high-speed performance due to their dedicated carry chain, which runs vertically in columns from one slice to the neighboring slice. So in this slide, we wanted to talk a little bit about the symmetrical layout of the routing and the logic resources available in the 7 series of FPGAs so that you can appreciate how it gives you improved density, saves metal routing resources by sharing clock lines in the FPGA, and this also, again, helps you improve the routability. So in this example, you see that each CLB has an associated switch matrix that will be responsible for connecting the CLB inputs and output signals to general interconnect and dedicated global routing resources. Now these are denoted by data lines and clock lines as seen in this figure. In the end, how you actually get a hold of this is invisible to the user since the implementation tools will optimize the place and routing solution for you. And again, we don't encourage designers to ever have to go in and try and control this, since it should not ever be something the user has to control. The tools, again, do a very good job of managing the grouping of your logic into CLBs and managing the routing solution of the implementation tools. The implementation tools select an appropriate routing that may include different kinds of routing resources. The solution that is routed is designed to try and meet your timing needs based on the timing constraints you enter with your design. This will allow the software to choose the most intelligent routing solution to meet your application's timing performance objectives. In fact, the mapping and placement of logical resources is handled by the program called PAR, the Placement and Routing Utility. The routing resources available to your design is fixed and optimized by Xilinx experts. The types of routing resources vary by length and refer to the number of columns or rows of CLBs they span. In Virtex 6 and the 7 series, all routing, besides the carry logic resources, is routed through the switch matrices. While understanding the interconnect structure is not needed, this diagram is meant to describe the population or the ability of the routing resources to interconnect between slices and CLBs. Now let's continue our discussion by looking at the slice resources that are contained within the CLBs. Now, combinatorial logic is stored in lookup tables or LUTs. Lookup tables are also sometimes called function generators in this industry. The capacity of a LUT is limited by the number of inputs, not by the logic complexity. so delay through the LUT is constant regardless of what logic function is being performed inside. Each slice contains a 6-input LUT that can also be broken into two 5-input LUTs. This allows the resource to be broken down if necessary to help assure maximum device utilization. Every customer must understand the input limiting nature of LUTs because many customers are used to building with ASICs. It is important to understand that the HDL code you write needs to be optimal for the FPGA if you're going to get optimum speed and device utilization. This is because ASICs are faster than FPGAs, and it's much easier to get good speed from an ASIC with suboptimal HDL coding styles used. Now, this is highlighted when you consider that you would get if your combinatorial logic had 7 inputs. Because the LUT has 6 inputs, your synthesis tool will be required to add a second LUT in series with the first. This would then dramatically increase the delay associated with this path and cut the maximum frequency possible for your design. Each CLB contains 2 slices. From this diagram, you can see that each slice has 4 LUTs, 4 flip-flops, and 4 additional flip-flops that can also be programmed as latches. The carry chain is connected to 4 of the 8 flip-flops. There are also dedicated muxes which can be used to build larger multiplexers and save LUTs so your system can run at a higher speed. This slide highlights the fact every 6-input LUT can be programmed as 2 5-input LUTs with a separate output. We added additional registers because the LUTs can be broken into 2 5-input LUTs, and this should help designers get more logic out of their FPGA design. In this diagram, we see a number of muxes. Each is used to connect the LUT outputs together. Each slice contains 2 F7 muxes that groups the outputs of 2 LUTs and can create an 8-to-1 multiplexer. Each slice also contains one F8 mux that combines the outputs of the F7 muxes and thus can build a 16-to-1 mux. The mux outputs can drive out of the slice or connect to the available flip-flop latch associated with each slice. These dedicated multiplexers are used to improve the speed of large multiplexers and save LUTs for other purposes. Be aware that if you're going to code for a large multiplexer, you must code with a case statement in your HDL. This is required if you expect your synthesis tool to infer this mux structure. Carry logic is the dedicated hardware resource that improves the speed of arithmetic functions such as adders, accumulators, subtractors, and comparators. From the diagram, you can see that the left-hand slices are grouped into one carry chain. Now please note that carry logic propagates the carry signal vertically upward. This is important to note because most designs use carry logic extensively, and by using it, the least significant bit should be placed at the bottom of the carry chain. Likewise, when carry logic is used, bit ordering should be followed by the designer, with the less significant bit being placed beneath the most significant bits. Each slice has 4 flip-flop latches and 4 flip-flops associated with the slice. The difference between them, besides their programmability as a latch, is that the flip-flop latches, seen here labeled FF/L, can be driven by the LUT carry chain or the wide multiplexers. Conversely, the flip-flop can only be driven by an O5 input, which can come from the 6-input LUT when it is used as 2 5-input LUTs, or from a separate input to the slice. Now, these limitations are not as big of a deal as you might think, however. But in the end, if you're building lots of lower input functions that share inputs, as is required to have the 6-input LUT broken into 2 5-input LUTs, you should end up with the flip-flops being used extensively like this. All flip-flops and flip-flop latches share the same control signals. The group of associated control signals with a flip-flop is important since only flip-flops that share the same control signals can be grouped into the same slice. This means that if you don't manage the use of your control signals and try to reduce the number of control signals your design has, then you might have trouble getting high device utilization. The set and the reset signals can be configured as synchronous or asynchronous on each flip-flop. For synchronous design purposes, Xilinx recommends that unless absolutely necessary, you design with a synchronous set or a synchronous reset. And we discuss good synchronous design practices in the Essentials of FPGA Design, as well as in our HDL coding styles, RELs. Now, to help designers with this, we have made a series of Vertex 6 and Spartan 6 HDL coding style RELs that are available to you to review at your leisure. They discuss the impact of the use of your coding style and provide you with many good design practices that will help you get high performance and high device utilization. So check those out. Even if you're using the 7 series, these techniques will still apply to the 7 series. Now we're going to have a short summary, but again, to hear the rest of the content intended for this module, don't forget to listen to part 2 of this recording learning. In summary, all slices contain 4 6-input LUTs and 8 registers. LUTs can perform any combinatorial function of up to 6 inputs or 2 functions of up to 5 inputs. 4 of the 8 registers can be used as flip-flops or latches. The remaining 4 can only be used as flip-flops. Now, the LUTs and register structures we've seen are designed to give you high performance as well as high device utilization, which also explains why they have so much flexibility. Now, the slices also contain carry logic resources and dedicated muxes, in particular the mux F7 and F8. The mux F7 will allow you to create 7 input functions or an 8-input multiplexer. Now, this will save you LUT resources. Likewise, the mux F8 combines the mux F7s to create 8-input functions or 16-input multiplexers. Again, likewise, saving you for having to cascade lots of lookup tables in series and getting you better performance and better device utilization. The carry logic can be used to implement fast addition, subtraction, and comparison functions as well as other arithmetic operations. And in the end, the reason it's so fast is, of course, because it has a dedicated routing resources as well as dedicated logic that are optimized for arithmetic operations. So now we're going to continue our discussion about the CLB contents by getting into distributed RAM and the shift register LUT resources. Many, but not all, LUTs in the FPGA can be configured for distributed RAM. Distributed memory is a configuration of the LUT so it behaves as a small 64-bit memory that can perform a single, dual, or quad port memory. Now, SLICEM slices are full slices where the LUT can be reconfigured as distributed memory or as a shift register LUT, denoted here in the diagram as an SRL. Slice Ls are LUTs that can only be used for logic, not memory, or for the shift register LUT functionality. As you can see from the figure, only CLBs labeled LM, which is 1/4 of the device CLBs, contain some CLBs that are SLICEMs. Each port of distributed memory has independent address inputs and has a synchronous write as well as an asynchronous read functionality. Now there are 4 configurations, as you can see. Most customers use these resources for DSP applications, but sometimes customers try to build larger memories out of these same memory resources. Now it is possible, but the extra logic to connect up all the lookup tables when configured for memory, when you connect those together, can actually make the performance of this larger memory prohibitive. So you may want to consider building a larger memory instead with the dedicated block RAM resources. After all, that's what they're there, dedicated in silicon for. But in general, those customers that build with distributed or block RAM memories are using the core generator or the system generator to build their DSP application. Those are the primary tools for targeting these resources. Many LUTs can be configured as a 32-bit shift register as well. Now, this is used primarily as a pipeline delay element for balancing pipelined applications, but it can also be used for variable length shift registers, synchronous FIFOs, CAMs, or pattern generators. Now, this resource, the shift register LUT, is cascadable to up to 128 bits in length. The most challenging thing with this is that most customers don't realize that this shift register LUT is not loadable, has no reset, and only offers serial in, serial out capabilities. So if you try to infer it with any of the corresponding behavioral code, your synthesis tool will infer regular registers, and that will be a big waste since you probably want to save the flip-flops for your application. So the benefit of using the shift register LUT is that it can effectively provide the work of 32 registers for a pipelined application within a single lookup table. So in pipeline applications, this is a huge savings and perfectly applicable when using the shift register LUT to pipeline your application. Now, this is an example of the use of a shift register LUT. Now, the SRL again can be used as a programmable delay element or a no operation or no op. In this example, you see a 64-bit bus being processed through operation A, B, and C. A has a delay of 8 cycles, B has a delay of 12 cycles, and C has a delay of 3 cycles. Now, because the data processed is also to be grouped at its output with a multiplexer, These data paths must synchronize so that the appropriate data is compared to the multiplexer. To do this, the shift register LUT can be used to delay the C operation by the necessary 17 clock cycles so that the data is synchronized. But if we were to do this with normal registers, it would require over 1,000 registers. If we use the shift register LUT functionality instead, we only need 64 LUTs, each programmed for 17 clock cycles of delay. So this example will use 64 LUTs to replace the over 1,000 flip-flops and the associated writing resources to complete this functionality. This is a very good justification for using the shift register LUT functionality. Because there are so many registers in FPGAs, pipelining is an effective way for designing to increase design performance, because these pipelines can sometimes become unbalanced when too much logic must be generated. It is necessary to delay some of the signals in very typical situations like you see here. One of the best uses of the SRL is to add delay to the balancer pipeline. Now let's continue with our discussion by looking at how you can use your SLICE resources. There are 3 ways to get the FPGA resources you need into your design. You can either infer logic with your synthesis tool, instantiate the necessary primitives from the Xilinx Unified Library, or instantiate an optimized component from the core generator or system generator into your application. This slide is intended to guide you to the proper HDL coding style so that you get what you want out of the FPGA. One of the biggest challenges for new users is to make certain that they are inferring the appropriate resources. First of all, one of the best ways to check that you're getting the resources inferred is to check with your tool's schematic viewer. That's your synthesis tool schematic viewer. You should use the technology viewer to understand what Xilinx primitives are inferred by your synthesis tool. A primitive is a resource that is written to the netlist that represents a LUT, a shift register LUT, a distributed RAM, a MUX. You get the idea. All primary SLICE resources can be inferred by XST as well as simplified. This includes LUTs, flip-flops, shift register LUTs, MUXes, and carry logic. However, you must be sure to code for the resources properly to get what you want. This means that if you define a flip-flop with an incompatible combination of control signals, you'll get something slightly different, probably with a LUT input used for a control signal. Likewise, the shift register LUT is non-loadable, has no reset, and again only supports the serial functionality. So if you code for a parallel read, you'll get a pure register implementation rather than getting the lookup table reprogrammed as the shift register LUT, and this won't be what you expect and will waste registers. Similarly, MUXes should use a case statement, and carry logic should use the proper arithmetic operator in the HDL code to infer it. Don't code for an XOR functionality with your HDL code and expect to get carry logic inferred. Now, in general, inference is best and preferred by our customers. It assures portability to another technology and is reusable. However, most customers will have to do some instantiation to optimize the design for any FPGA on the market. So it's important for users to understand that there may be times when they have to instantiate the resource, or at least they're going to have to optimize their HDL code to get the most out of the FPGA. A list of Xilinx primitives and their behavior can be found from the libraries guide. This is available at support.xilinx.com or can be found from the help menu in the ISC software. This will describe all the ports and attributes that can be customized by you. There is also a complete description of the XST attributes located from the software manual's webpage. This is also a useful resource for understanding how to infer logic. The core generator and architecture wizard make larger optimized components easily available. While some cores have a charge associated with them, most do not have a charge. The cores range from simple components to large, highly complex IP. The architecture wizard is used most commonly to customize DCM and PLL components that you may use in your FPGA. The core generator and architecture wizard help you instantiate a high-level component and make it easy to customize that component for your applications. Now, these cores are optimized and make designing for all the detailed functionality of things like the DCMs and PLLs much easier. They also provide access to some very powerful design tools that can create common, sophisticated components at no extra charge. So let's wrap up our discussion with a brief summary. In summary, the LUTs in the SLICEM slices can also be used to build 32-bit shift registers or small 64-bit memories. And we discussed the reasons why you want to build shift registers for pipeline applications and why, if you're building a small memory or DSP application, use of these LUTs to configure 64-bit memories can be very helpful. Slice resources are most commonly inferred by synthesis tools, but can be instantiated or accessed via the core generator, architecture wizard, or the system generator utilities. Well, there's lots of useful information about inference and synthesis attributes in the Synthesis and Simulation Design Guide. It is available from the ISE software using its help menu or directly from support.xilinx.com. So if you don't find it with the tool, then again, you go to the website and you can find it there. Now, the XST User Guide also provides very helpful coding recommendations that all Xilinx users should live by. It also includes a detailed description about all of XST's synthesis options. This information can also be found from the help menu. And as I mentioned, though, probably one of the more important things is to go look at the 7 Series or the Vertex 6 HDL coding techniques, RALs. Very helpful on learning how to optimize your code for the architecture. If you would like to see what other courses we offer or what other free RALs are available, go to the Xilinx Education link you see here. I'd also like to mention again that there are architecture modules available that discuss the basics of Xilinx's newest devices. You may find this useful, especially if you want to learn more about the device differences. But whatever you do, please take a second and let us know what you thought of this recorded e-learning module. Just click on the icon on the next page and tell us what you think. Again, my name is Frank Nelson. You've been listening to the basic CLB Architecture module for the 7 Series FPGAs, Part 2. Thanks for listening, and thanks for your business.